part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to be working through 3 different examples of dielectric boundary value problems. In the first case, we'll look at a dielectric sphere that's placed in an otherwise uniform electric field. The second example that I'm going to work is a point charge placed in a dielectric medium that occupies z greater than 0 space, and another dielectric medium occupies the other half space. And in the third example, I'll work as a dipole placed at the center of a dielectric sphere. So let's get started straight away. Here's our linear isotropic sphere, characterized by a dielectric constant K. And there's our uniform electric field pointing in the z direction. As you get very far away from the sphere, you'd expect there to be negligible influence on the applied uniform field. Close up, of course, you'll see much greater distortion. So where do I begin? If you do this problem seems familiar to you, it should. We worked an example where we had a conducting sphere, a grounded conducting sphere, placed in an otherwise uniform electric field. So how we tackled that problem was to write down an expression for the potential. Now remember, we are in undergraduate electromagnetism, so we deal only with problems that present azimuthal symmetry. So in other words, the potential is only going to be a function of the radius r and the polar angle theta. In such cases, you can write your solution as a form of some constant al times r dl plus bl times r to the minus l plus 1 times the Legendre polynomial. And we also have certain boundary conditions as well. First case, the potential is continuous across the boundary. So in other words, the potential inside is equal to the potential outside. We evaluate those expressions at the radius of the sphere. Second condition is that there's a discontinuity in the normal component of the displacement field at the radius of the sphere, and that discontinuity is equal to these free surface charge density. Now in this case, there is no free surface charge density, or there's no free charge at all. So for this particular example, not generally speaking, the normal component of the displacement field is continuous. But again, I emphasize only for this problem, not generally speaking. Okay? So what other conditions do we need to impose upon the solution? Well, for one thing, we know that the solution has to remain finite in the respective regions. So in other words, if you look at the interior solution, that can't blow up as r goes to 0. So therefore, we're going to set all the BL terms, BL coefficients equal to 0. So therefore, inside, solution can be written as a summation L equals 0 to infinity, eighth of L, R to the L, PL cosine theta. Now notice I put a superscript up there, a less than sign, just to indicate or to distinguish between sets of coefficients. I'll drop it later on, but I'm just going to put it up there for now. Okay, in the greater than region, solution also has to remain finite as r goes to infinity. So that means that all the coefficients base of L have to be set to 0 because you don't want your solution to blow up as r approaches infinity, with the exception of one term. because your electric field goes as E naught Z as you get very, very far away, that tells you that your potential is going to go as minus E naught R cosine theta. So in fact, you will have one surviving term of the A's of L's, and as a matter of fact, that's just going to correspond to the L equals 1 term. So the first order Legendre polynomial is just equal to cosine theta. So therefore, we've got minus E naught R cosine theta. So basically, we're just setting our coefficient, A sub 1 greater than equal to this. Okay. So we've eliminated an infinity of coefficients already. Where else? What else can we do? Well, we know this has to remain constant across the interface, and we know the normal component of the displacement field also has to be constant across the interface as well. If you recall back to when we first started doing boundary value problems, we made use of the orthogonality of these functions, and because we've got this cosine theta term over here, this has to hold. These expressions have to hold for all thetas. The only way that's going to happen is if we've only got that cosine theta term in our expansion. So the only one that survives on account of orthogonality is A1 less than R cosine theta. And then here we have B1 greater than over R squared cosine theta. Now I could go through and put on all the bells and whistles and actually do the integration there, but it's just easier if we just recall that the only surviving term is going to be a cosine theta term. Remember, with zeroth order, Legendre polynomial is just equal to 1 first, cosine theta, and second is equal to 3 cosine squared theta minus 1 over 2, and so forth. Okay? We've had an infinite number of possibilities here. We've reduced it to 2 unknowns, and we've got 2 conditions yet to satisfy: the continuity of the potential, and in this particular case, the continuity of the normal component of the displacement field. I'm going to go ahead and drop the superscripts and subscripts as well. I don't need them anymore. So, first condition. Potential continuous at R equals A implies that A1 capital R cosine theta is equal to B, and I said I was going to drop the subscript, so I'm going to do that, B over R squared, radius squared cosine theta, minus E naught R cosine theta. Cosine thetas drop out, and I'll be left with A is equal to B over the radius of the sphere cubed minus E naught. We get one expression, one equation relating to 2 coefficients. Now I'm going to apply the condition that the normal component of the displacement field is continuous in this case because there's no free charge, and certainly no free surface charge density. I can write this in terms of the electric field. In this case, we just have the permittivity of free space outside, so it's epsilon naught. And over the right-hand side, the permittivity of the matter inside the sphere is equal to the dielectric constant K times the permittivity of free space. So that's E less than, and those have to be continuous at the boundary of the sphere. Now, if I take, write this in terms of the potential, this is the partial derivative of the potential with respect to the normal. And remember, that's the minus, electric field is equal to minus the gradient. And we're taking the normal component, essentially, of minus the gradient. So the minus signs drop out, and we'll be left with partial derivative of the potential outside with respect to the normal is equal to the dielectric constant times the partial derivative of the interior solution with respect to the normal, and that has to be continuous across the boundary of the sphere. Okay? And the normal component in this case is just the radial component, so therefore, applying my second boundary condition, it implies that we have Ka cosine theta is equal to minus b 2b over r cubed cosine theta minus e naught cosine theta. All the factors cosine thetas cancel out, and we'll be left with Ka is equal to minus 2b over r cubed minus e naught. And that's just a question of solving these two couple equations. And if I multiply the first equation 3 by 2 and add these up, I can eliminate b. And therefore, the coefficient A is equal to minus 3 E naught over K plus 2. And I can plug this, I can do either one of these, I'll do it in the first because that's easier. Therefore, I can multiply that first equation by R cubed and move the E naught over to the other side. And I wind up with coefficient B is equal to K minus 1 over K plus 2 times E naught, magnitude of the uniform electric field, times R cubed. Plug these two coefficients back into my expression, and therefore the interior solution is equal to minus 3 E naught over K plus 2 times R cosine theta. The exterior solution is equal to minus E naught R cosine theta plus K minus 1 over K plus 2 times E naught radius of the sphere cubed over the radius of the evaluation point r squared times cosine theta. And that's your solution. Now remember before when we were doing the problem of the conducting sphere, the sphere was grounded, so therefore the potential at the surface of the sphere and inside was equal to 0. And as you got very, very far away from the sphere, the potential went as minus E naught r cosine theta. In this case, we go to dielectrics, so you do have a non-vanishing potential inside, and it does depend on the radius at which you're evaluating the field, or the potential, and also the angle. Now, it should be the case that if we assume that our dielectric sphere has a very high dielectric constant, essentially, let's assume that our sphere is conducting, becoming a conductor, these answers here should go over to the answers that we got for, we just assumed we had a conducting sphere. So in other words, if we assume K gets infinitely large, I should get the same answer as I did before. Okay, so if K gets very, very large in this first part, V less than is just going to go to 0. All right, you get 1 over K, so no matter what R and cosine theta are, K dominates, so therefore the interior solution is 0. Now the exterior solution, that first term is unaffected as it should be, minus E naught R cosine theta. And in the last term, if K gets very, very large, these 1 and the 2 are negligible in comparison, so basically the K's cancel out and we'll be left with E naught radius cubed over R squared cosine theta. So you can see that in the limit of a very large K, that the solution goes over to that of a grounded conducting sphere in an otherwise uniform electric field. Okay? And I'll just leave it up there for a minute. And we'll move on. The next example that I'm going to consider is an image problem. I've got 2 dielectric media. One occupies the upper half space, in other words, Z greater than 0, and the other dielectric media occupies the lower half space. And I want to figure out what is the potential due to a point charge in this particular system. I'm going to handle this using the method of images, and in this case, it's a good idea to step back and look at how we solve those problems when we were just dealing with vacuum, okay? So recall this one. You had a charged particle in the presence of a conducting plane, and the problem there was to figure out what is the potential in the upper half of the plane. So how we began with that was to say, got some potential and get a point charge, so that's going to be part of our solution. It's Q over 4 pi epsilon naught R minus R prime. And there had to be some other function such that the boundary condition is satisfied. The boundary condition being that V vanishes at Z equals 0. And we assumed our charged particle was a distance d above the plane. And remember from the uniqueness theorem, tells us that if you find a solution that satisfies the boundary conditions, you are guaranteed that you have found the one and true solution. What we did there was to replace this boundary, this grounded plane, by an image charge. Now remember, the image charge isn't actually there, okay? It's just a method for solving this problem. So we're replacing this problem with this one. And as a result, we figured out, well, this charge has to have the same magnitude as the first one. and also that it's going to lie the same distance away from the plane. So therefore, the potential was equal to Q over 4 pi epsilon naught square root of x squared plus y squared plus z minus d squared. That's your real charge. Your image charge is equal to minus Q over 4 pi epsilon naught x squared plus y squared plus z plus d squared. When you handle this problem, it was best to figure out where the charge exists, where you should put your image charge first, and then determine what the value of the charge actually has to be. So I'm going to take this lesson of solving this problem and apply it over here. I've got a charge. What's the potential due to a point charge in a dielectric medium? So for now, I'm going to forget about this K2 region, okay? I just want to figure out what's this potential due to this charge, this isolated charge, in some medium K1, okay? Well, the electric field due to that, and we'll say this is the origin here, it's a distance d above the plane. So the electric field due to that charge is going to be equal to Q over r minus r prime over 4 pi epsilon naught r minus r prime quantity cubed. We're putting our charge at the position x equals 0, y is equals to 0, and z is equal to d. And also, because we are dealing with dielectric media here, the electric field is shielded. Its actual strength is reduced, so we got a factor of k there in the denominator. If you were to apply Gauss's law to this, you'd have Q over 4 pi k epsilon naught. Okay? Okay, so this is Q, and we're evaluating this at x is caret plus y caret plus z minus d z caret all over 4 pi ep k epsilon naught x squared plus y squared plus z minus d squared to 3/2. So you know what my electric field is. If you have an isolated charge in a dielectric medium, and therefore I can figure out what the potential is. Potential is just equal to the interval. If I take the line interval from infinity to some point r, point of observation r, I'll find that the potential due to this isolated point charge is equal to Q over 4 pi k epsilon naught square root of x squared plus y squared plus z minus d. Okay? So that's my charge, isolated charge in the medium K1. Now, of course, I want to go back to my problem. I've got a charge that's in the K equals K1 space, but I've also got an infinite half space of dielectric medium K2. So how do I handle this? Well, I'm going to replace this K2 with an image charge. And I'm going to assume that the whole universe, if you will, is occupied by a dielectric medium K1. And I'll call this charge Q prime and some distance d away from the interface, okay? So I'm looking for the solution in the region above the interface, and I'm asserting that I can replace this by this. So in other words, we're removing, forgetting about K2, but we're introducing this charge Q prime that has some value in some location such that this is the same as this in the upper half plane, okay? So therefore, I'm no longer talking about an isolated point charge. I have another charge to deal with, and there should be a little subscript 1 always. Okay, so it's 4 pi k1 epsilon naught x squared minus x prime squared plus y minus y prime squared plus z minus z prime squared. First order of business in determining about this charge and where it's located is to figure out first, where should we put it? Well, it makes sense that this would lie along the same line that joins Q to the interface. So we're going to draw this line such that this is perpendicular to the interface. So in that case, it tells me that my charge Q prime should be lying along the same axis. So that's x squared plus y squared plus z minus something or other. Okay. So I'm going to assert once more that, well, it makes sense. You know, if this is d above, why not take this d below? So that's plus d. And as I mentioned before, solving problems by the method of images involves intuition into how these charges behave. So that's why I think sometimes these problems can be conceptually difficult, because you kind of have to have a feel for how things behave in order to come up with a reasonable expression to satisfy the boundary conditions. Okay? And really the proof is in the pudding. If my expression satisfies the boundary conditions, then I'm good to go. If not, well, I've run into trouble. Okay, so anyway, this is the potential above the plane. So I'm going to put a little caret, a little subscript greater than to indicate this is a solution that satisfies this problem in the upper half space. Before, we didn't need to worry about below the plane, right? Because this is grounded. We were only concerned with the solution above. But because you have a dielectric medium, well, the potential doesn't vanish beneath this interface. It has some value. And I'm going to assert that for the less than region, I can replace this by an image charge. So in other words, instead of assuming that the whole world is occupied by dielectric medium K1, I'm going to assume that the whole world is occupied by medium K2. And where do I put my image charge? Now remember, the problem, or the feature of solving images problems is that you can't place your image charge where you're solving for it. So in other words, our image charge was in the region that we didn't care about. It was below the plane, okay? Over here, and the first, we're solving for the solution above the interface. The image charge, we're putting that below the interface. Now over here, okay, so we're solving for the potential down below. So where's the image charge go? It's got to go above. So it's up here. And we'll call it Q double prime. And the question is, where do we put our image charge Q double prime? Well, I'm going to assert once again that it should lie on the same axis as Q and Q prime, so therefore we radical is going to be x squared plus y squared. Now the last question is, where along the z-axis do we put it? Well, I'm going to assert that, well, this charge is going to occupy the same position as my real physical charge, okay? So let me go over the reasoning behind this again. Reasoning why I'm choosing my potentials to have these forms. And once I apply the boundary conditions, if I come up with a solution here, I'm guaranteed that I found the one and only solution, okay? So in the first case, we're going to replace this interface with a little dotted line here. We're going to replace it with the Q, image charge Q prime. So here we're assuming that I can solve this problem in the upper half space if I assume that the entire universe is occupied by dielectric medium K1 and some image charge Q prime located the same distance d away from the interface. Okay, that's my solution above. My solution below, I'm going to replace the interface. I'm going to assume that the whole world is occupied by dielectric medium K2 and that there's an image charge that exists where my real physical charge is. So that's my expression for the potential below the plane. Now, what are the boundary conditions? Let me erase this over here. give myself a little bit more room. The potential must be continuous across the boundary, so the boundary we're talking about is z equals 0. And the other condition is that, generally speaking, there's a discontinuity in the displacement. However, actually we should write that the other way around. However, because there is no free surface charge density in this example, that's equal to 0. Now, of course, there's going to be bound charge. There's going to be bound charge right around this charge Q. There's going to be bound charge right above the interface and bound charge right below the interface. Applying my first condition. If I set z equals to 0 in all these, I'll see that I'll have square root of x squared plus y squared plus plus d squared in the denominator. Maybe I'll just write it out just for make sure I don't rush over anything. So we'll have 4 pi k2 epsilon naught square root of x squared plus y squared plus d squared is equal to q double prime is equal to q over 4 pi k1 epsilon naught x squared plus y squared plus d squared. And image charge q prime over 4 pi k1 epsilon naught x squared plus y squared plus d squared. So all of these three terms have in common this square root of x squared plus y squared plus d squared, 4 pi epsilon naught as well, and I'll be left with a nice simple little equation. Q double prime over k2 is equal to q over k1 plus q prime over k1. It's my first boundary condition. Second boundary condition is that the displacement, in this particular example, the normal component of the displacement is continuous. So that is the same thing as saying k1 partial derivative of v greater than with respect to the normal is equal to k2 times partial derivative of below the interface with respect to the normal. And maybe I should write it the other way to make sure I'm consistent with how I set that up. So I'll put k2 over here and k1 on the left hand side. Take the derivative with respect to z. That is equal to q first term will give me q times minus 1/2 times 2 times z minus d over 4 pi epsilon naught x squared plus y squared plus z minus d squared all to the 3/2. And a similar expression for the second term and also for a third term. And that holds at the interface z equals 0. In that case, all the 4 pi epsilon naughts, the q, not the q's, the x squared plus y squared, and you'll be left with the d squared in the denominator. All those terms are going to drop out. The z's are all going to be 0 up there, so you'll wind up with q times minus q plus q, and minus q prime is q double prime. Anyway, I said I was writing it the right way, and I had it the right way before, but it doesn't matter. We've got 2 equations and 2 unknowns. Okay? We solve this for q prime and q double prime. And sadly, I'm going to have to erase a lot of this to give myself some room. Reduce all this horrid looking mess to 2 nice little equations. Let's see, we divide the first equation through by k1 and add these 2 up. We will be left with this plus this, so this will be 2q over k1. Second term drops out. We'll have minus q prime over k1 plus q prime over k1. And then we'll have 1 over k1 plus 1 over k2 times q double prime. Q double prime has magnitude of 2q k2 over k1 plus k2. Q prime is equal to q minus q double prime, and that's equal to k1 minus k2 over k1 plus k2 times q. And therefore, I can write my solution out above the interface. The potential is equal to q over 4 pi k1 epsilon naught square root of x squared plus y squared plus z minus d squared plus q. This is our image charge now. This is image charge q prime times k1 minus k2 over k1 plus k2 times q. Over 4 pi epsilon naught, and I don't need to have 2 q's up there. 4 pi epsilon k1 epsilon naught, x squared plus y squared plus z squared. That's the solution above. The solution below, it's as if we replace the interface by some other charge q double prime that exists in universe of dielectric medium k2, and that is equal to 2q k2 over 4 pi epsilon naught K2, K1 plus K2, x squared plus y squared plus z minus d squared. And these K2s will cancel out. And that is your solution. So this is kind of a difficult problem because, like I said, it requires insight. It's always a good idea to use what you know as a guide. So let's see if this collapses to the right value if we assume that K2 is infinitely large. So in other words, if below we've got just a conducting plane. So what happens there? Well, if K2 gets very large, this one below is going to go to 0. Above, however, we're going to wind up with and let's assume that we've got a vacuum above. So we've got a vacuum above and a conductor below. So this goes to Q over 4 pi epsilon naught square root of x squared plus y squared plus z minus d squared. This term over here, we're taking K1 equal to 1, K2 goes to infinity. So those terms are negligible in comparison, and we wind up with a minus Q over 4 pi epsilon naught square root of x squared plus y squared plus z plus d squared. So happily we're getting our results. If you consider this to be a charged particle in a vacuum over a conducting plane. So, but anyway, this is your answer. If you've got a point charge Q, dielectric medium K1 occupying the upper half space, and K2 occupying the lower half space. Okay. In this third and final example, we'll consider the case of a dipole placed at the center of a dielectric sphere. I want to determine the potential both in the interior region and the exterior region. Since this problem presents a degree of spherical symmetry, I'm going to expand the potential in Legendre polynomials. So therefore, the solution, generally speaking, can be written as summation L equals 0 to infinity, A sub L times R to the L plus B sub L R to the minus L plus 1 times the Legendre polynomial PL cosine theta. We need to apply the boundary conditions. So as usual, the potential is continuous across the boundary. So in other words, the interior solution equals the exterior solution at the radius of the sphere. The other condition is there's a discontinuity, generally speaking, in the displacement if there happens to be free surface charge density. Well, there isn't in this case, so therefore in fact, the normal component of the displacement vector across the boundary is continuous. And written in terms of skipping a few steps and writing this in terms of the potential, we have K times the partial derivative of the interior solution with respect to the normal is equal to the partial derivative of the exterior solution with respect to the normal evaluated at the surface of the sphere. Okay? Or I should say the radius r. Okay, so let's set about constructing our solutions. Now the first thing you want to notice here is that you've got a dipole. So there is going to be a dipole contribution to your expansion. So just as a reminder, potential due to an isolated dipole is equal to P dot the separation vector over 4 pi epsilon naught times the magnitude of the separation vector cubed. In this case, we're placing the dipole at the origin, so therefore r prime is equal to 0. Moreover, we'll assume that the dipole is pointing in the z direction. So therefore, we'll have P z dot r, and the only term that will survive from radius vector is the z term, and that's just going to give us PR cosine theta over 4 pi epsilon naught r cubed. Now, I'm just going to go ahead and factor out one of the r's, so we'll take out the r from the numerator, and that becomes r squared in the denominator. Now, what other point do I need to make here? Well, the dipole is not simply in a vacuum, it's in dielectric. So the effect of the dipole, the field from it, will be shielded, and also the potential will be reduced by a factor of k. So we now have, for a dipole placed at the center of a linear isotropic dielectric sphere, is going to be P cosine theta 4 pi k epsilon naught r squared. So therefore, for our interior solution, we will have this term. In fact, that will be the only term that survives from the r minus l plus 1. After all, we want our solution to converge and be well behaved. So therefore, that rest of the r's, BL's are going to vanish in that case. And we'll be left over with summation L equals 0 to infinity times the coefficients AL, RDL, PL cosine theta. I'll put a little superscript less than up there to, just for the time being, to distinguish between the coefficients that pertain to the interior solution and the coefficients that pertain to the exterior solution. Now, in the exterior region, again, we need to have a finite solution, so therefore, all those AL terms will be set to 0, and we'll be left with summation L equals 0, BL greater than R to the minus L plus 1, PL cosine theta. Now, this is a little different from the other example I worked earlier, because in that case you had a dielectric sphere that was placed in an otherwise uniform electric field. So you had an extra term here due to that uniform field, but that's not happening in this case. So we've got our dipole plus whatever contributions we have from this summation in the interior region, and then our exterior solution goes as r over minus L plus 1 PL cosine theta. So now let's apply the two boundary conditions to see what see where things go. Okay, so hold for all theta. So therefore, when I do the math, what I'll see is that because of the orthogonality of the Legendre polynomials, only one term is going to survive from this summation, and only one term is going to survive from that summation. We covered this in greater detail when we first discussed boundary value problems in spherical coordinates, and we made use of the orthogonality to eliminate a lot of the, or virtually an infinite number of coefficients. So the only surviving term in that from this summation is going to be the L equals 1 term, and the only surviving term here will likewise be the L equals 1 term, because remember, for your Legendre polynomials, the 0th order is 1. First order is cosine theta. Second order is 3 cosine squared theta minus 1 over 2, and so forth. So the only surviving terms, therefore, will be the terms that correspond to the first order cosine theta, so L equals 1. So therefore, for my interior solution, I will have that first term and a r cosine theta. And here, this is really have a 1 and a superscript less than, but I'm going to drop that so there's no, because there is no chance for confusion now. And then for the greater than solution, we'll have b cosine theta over r squared, and I'm going to apply both of these boundary conditions to solve for the two unknowns. So in the first case, we have p cosine theta over 4 pi k epsilon naught radius of the sphere squared plus a r cosine theta is equal to b cosine theta radius of the sphere squared. Each term has a common factor cosine theta, so those all drop out. If I divide by a, or rather r, I can wind up with a is equal to b over r cubed minus p over 4 pi k epsilon naught radius of the sphere cubed. Now I'm going to apply the condition that the displacement be continuous across the boundary. Remember, generally speaking, that's not the case if you have free surface charge density. There will be a discontinuity. There is no free surface charge density in this example, so therefore it is continuous. We'll have k minus 2k p cosine theta over 4 pi k epsilon naught r cubed. The k's drop out. A cosine theta, and then on the right hand side, can't leave off the k here. And on the right hand side, we'll have b cosine theta over r cubed. So once again, all the cosine thetas drop out. Each term has that factor in common. And I can write this as Ka. And actually there's a minus 2 there as well, because we're taking the derivative of the exterior potential with respect to r. So it's now the 2 in the numerator, minus 2 in the numerator. These are my two equations, and the the two unknowns, A and B. Unfortunately, I have to erase some of this because I don't have quite enough room. So I'm going to go ahead and multiply the first equation through by 2 and add them up. The b terms will drop out. And from the two dipole terms, we'll wind up with 2p over 4 pi epsilon naught r cubed, parentheses 1 minus 1 over k. And therefore the coefficient A is equal to P over 2 pi k epsilon naught radius of the sphere cubed times k minus 1 over k plus 2. Now I want to solve for B. A little bit of algebra, we wind up with P over 4 pi k epsilon naught brackets 2 times k minus 1 over k plus 2 plus k plus 2 over k plus 2. So basically just adding 1 there. And therefore, this, you'll have a minus 2 in the numerator and a plus 2. Those will cancel out. And then I'll also have a 2k plus a k, which is going to be 3k. And that will cancel this k in the denominator. And I'll be left with k plus 2 in the denominator. Okay, so we've got 2k minus 2 plus k plus 2. That gives me 3k in the numerator. So it's a 3 here. That k cancels with this one. And we're left over with the k plus 2 in the denominator. Therefore, the final solution is p cosine theta 4 pi k epsilon naught r squared. That's the dipole term. And now the effect of the shielding gives rise to this term, PR cosine theta over 2 pi k epsilon naught r cubed times k minus 1 over k plus 2, and then the exterior solution. Goes as 3p cosine theta over 4 pi times k plus 2 times the permittivity of free space times r squared. So that is how you solve for the problem of a dipole placed at the center of a linear dielectric, linear isotropic dielectric sphere. And remember, you've got that dipole term. And then we want to apply the boundary conditions. First of all, that the potential be continuous across, when you go from the interior region to the exterior region. And also that, in fact, for this case, that the displacement is also going to be continuous. Generally speaking, it is not. There's a discontinuity, remember, if you happen to have a free surface charge, but there isn't in this case. So that is your answer. And that concludes today's lecture on solving boundary value problems in linear isotropic dielectrics.